So we have studied both atomic gas lasers and ion lasers. Next to follow should logically be molecular gas lasers. However, to understand the working of molecular gas lasers, it would be essential to have a basic knowledge on molecular spectroscopy. We would therefore get into the working or operation of molecular lasers later on in this course. So now let us turn into the other class of lasers, which are liquid lasers. You see, liquid lasers have inbuilt ability to provide continuous tunable output. However, no research activity took place until 1965 on liquid lasers. See, laser was invented in 1960. So for almost 5 years, there was hardly any work that was carried out on liquid lasers. Until then, that is until 1965, research was mainly focused to obtain newer transitions in gaseous and solid state. And of course, laser inventory grew leaps and bounds during this period. And as a matter of fact, by 1965, coherent light was available covering wide range of infrared, visible, and near UV. Near UV, of course, came from ion lasers. And this resulted in numerous applications to all branches of science and engineering. Only exception was spectroscopy, that essentially requires a continuously tunable source of light. Let me explain very briefly why the science of spectroscopy requires a continuously tunable source of light. And we need to know more because the liquid lasers which we will be now studying gives continuously tunable source. You see, spectroscopy is the science of mapping energy levels of atoms or molecules, which of course make up a medium, constitute a medium. So how do you do this mapping? And how spectroscopy works? Let us assume that you have, say, a gaseous sample comprised of atoms. Now these atoms, as you know, have energy levels. You know from both atomic theory that it will have electronic energy. Suppose this particular atom has this kind of energy. This is the ground state. And suppose it has two more energy. And the separation of these energy levels, so suppose this we call E0, this energy level we call E1, this we call E2. So E1 minus E0 corresponds to, this transition corresponds to light of wavelength lambda 1. That means if this transition gives a photon, photon will have a wavelength lambda 1, which is hc by lambda. And similarly, this transition E2 to EG gives out photon of wavelength lambda 2. And as you can see clearly, lambda 2 is less than lambda 1 because this energy difference is more than this energy. So lambda 1 is more. But how do you find out that this atom has this kind of energy level configuration? For this, you will have to do some spectroscopic study. How do you do that? Suppose you take a laser and suppose it is not a tunable laser, it gives out light, a beam of light of some wavelength lambda. You do not know some wavelength lambda. And so if you put a detector, this is a continuous laser, detector is monitoring the output. So if you plot the power as a function of time, the laser will emit continuous light in time, continuous power. It is a continuous loop. Now, you want to know if this atom has this kind of some energy configuration that you want. So then you will make this light intercept. So you will bring this cell containing the gas, bring it in the path of the light. If wavelength of the light doesn't match with any of these wavelengths, it will pass without any absorption. So it will continue to give you the same power. However, if suppose it so happens that this laser emits a wavelength lambda 1, then light of this wavelength, photon of this wavelength, the atoms in the ground state will absorb this photon and climb up. So photons from this beam will be absorbed. So the detector will record lower power. So suppose at this instant, at time, you have brought this cell in the path of the light beam. So here, there will be a drop in power. So then you know that if laser's wavelength is lambda 1, and by bringing this cell in the path of that light beam, there has been an absorption. You know that there exists an energy level which is separated from the ground level by an energy which is equal to hc by lambda 1. But if you do not have a continuously tunable laser, if you have a laser which gives discrete light, then it will be just a pure coincidence if you hit upon such a condition. You will have to, if the laser gives discrete light, you will have to just keep on changing the laser until and unless you find such a hit. So what is the remedy? Remedy will be obviously to use a laser which gives continuously tunable output in wavelength. So this laser, if this output can be tuned say from wavelength, say lambda 0 to say lambda 3. And say lambda 1 and lambda 2 lies somewhere in between. This is lambda 1, this is lambda 2, corresponding to which there exists some energy level in this atom. So how then you will do the measurement? Your study now. You will put your this cell here. On the other side of the cell, you will put your detector, and the output that the detector will record, you will monitor as a function of the wavelength of this light. So you begin from the wavelength lambda 0 to lambda 0. At lambda 0 corresponding to that there is no energy level, so there are many absorption. So the detector will measure high intensity, high power. Now as you are tuning your wavelength, at this wavelength, which is lambda 1, all of a sudden there will be an absorption. So there will be a reduction in the power that it records. There has been an absorption. Now as you continue to tune, suppose this is lambda 2. So at lambda 2 there will again be another. So you see now, if you have a continuously tunable laser, then by making use of this laser, you can very easily, very readily map the energy levels of these atoms. So that is why continuously tunable laser is important as far as spectroscopic study is concerned. And as a matter of fact, advent of liquid laser has very strongly impacted the science of spectroscopy and opened up a new branch of spectroscopy which we can call laser spectroscopy. All right. With this small introduction, let us get into the working of liquid laser. But before that, let us see what are the limitations of gas and solid state laser that would not allow their operation to provide continuously tunable light. You see, lasing transitions of atomic or ionic gas lasers are purely electronic in origin, because electrons' energy levels are involved in the operation of these lasers. We know that. In case of atomic gas laser, it is the neutral atoms' electronic energy level which participate in the process of lasing. And in case of ionic laser, it is the electronic level of the ions which participate in the process of lasing. But nevertheless, the energy levels are discrete in nature. So if the energy levels are discrete, you cannot obtain continuously tunable. The output too will be of discrete nature. This is your ground state, and these are the electronically excited state. So these transitions, as these are discrete, these transitions will give you light which is also will be discrete. Unless these are broadened So for example, this level is broadened in wavelength, in energy. Then you can tune. If the emission occurs from this point, you will generate a wavelength which is say lambda 1. And if the emission occurs from transition from this point to this, then suppose this gives a wavelength lambda 1 and this gives a wavelength lambda 2. And if the emission originates from any point in between these two, then you will generate light which will lie between lambda 2 and lambda 1. You will generate light of all these wavelengths. I hope you have understood that how can you get a continuous tunable wave. You need such a feature in your energy level. But because atomic lasers or ionic lasers would not offer you this advantage, these are all discrete level. So the wavelength that will generate or the frequency of light that will generate, this will be discrete. Now consider the case of a molecule. See, molecule will have its electronic energy level as well. But molecules have an advantage. It comprises of atoms. These atoms constitute of atoms. The atoms can both vibrate about the center of mass. Let us consider, say, nitrogen atom, nitrogen molecule. Two nitrogen atoms when are bonded together gives you nitrogen molecule. But this nitrogen atoms can actually vibrate about the center of mass, or they can even rotate about the internuclear axis. Therefore, in addition to electronic transition, a molecule also exhibits rotational and vibrational transitions. And these rotational and vibrational energies are much less than the energy required to excite an electron. Meaning that the spacing between the rotational energy levels, vibrational energy levels are much less compared to the electronic energy transitions. However, although they are much closely spaced in wavelength compared to electronic transitions, they really do not overlap at the typical gas pressures. If you increase the gas pressure, then there will be broadening of these transitions. You know, pressure broadening. We discussed pressure broadening. Only under prohibitively high operating pressure, at prohibitively high operating pressure, the individual transitions may be broadened so much so that they may merge together, give you a continuity. However, at normal operating pressure, even though they are much closely spaced compared to electronic transitions, they do not really overlap to provide continuous tunability. Therefore, the molecular gas lasers emit also discrete wavelengths, not continuously. In a solid, on the other hand, the atoms molecules are extremely closely packed in a solid. And if they're closely packed, they would not be allowed to vibrate or rotate, obviously, and therefore not free to move, thus exhibit only electronic transitions, and therefore once again discrete. Continuous tunability is not possible. A solid-state laser is therefore normally not conducive to rendering tunable emission, just like atomic ionic gases. Let us now turn our attention to a liquid medium. In a liquid medium, the molecules are not as tightly packed as in case of solids. You know that they're flexible enough to exhibit both vibrational and rotational motion. Thus, each electronic level of a molecule will be associated with many vibrational and rotational levels, similar to a gaseous molecule in a liquid. And if the molecule happens to be very large, that means it comprises of many atoms, very large molecule. So then there will be vibrational motions involving many atoms. There will be many degrees of vibration. So there will be many vibrational modes. So they will really pack up the intermediate spaces very greatly. And then the rotational levels also will also be present. And they tend to be enormous, very closely spaced. So closely spaced that they can merge together, giving rise to the prospect of providing continuously tunable light. I hope you have understood that how a liquid, and in particular of molecule that comprises of many heavy molecule comprising of many atoms, which will have numerous vibrational or rotational degrees of motion, can pack the intermediate spaces so enormously that it will give rise to continuity, closely spaced, with the prospect of providing continuously tunable. The very first liquid, European chelate, a metallo-organic compound, heavy molecule, large molecule, served as the medium for the very first liquid laser. It was, of course, to work like a liquid medium, it was dissolved in a solvent, this European chelate molecule. And a conventional spiral flash lamp was used as the pump source. The pumping was optical, and a spiral flash lamp, the same kind of flash lamp that Neumann used for the invention of the first laser, also was used here to pump this medium, liquid medium. And the pulsed operation of the laser was realized in 1965, 5 years after the invention of the first laser, very first liquid laser. However, the true potential of a liquid medium was revealed when organic dye molecules made their appearance in 1966. And it made a very great impact as far as continuously tunable light source is concerned. So let us turn our attention to the operation of a dye laser, working of dye laser. The dye laser was invented independently by Peter Sorkin, an American-Russian physicist, and Friedrich Peter Schaeffer, a German physicist, in 1966. Liquid solutions of organic dye compounds, perform the role of the active medium in these efforts. In their work, a ruby laser was used as the pump source, while the first dye laser used a flash lamp, spiral flash lamp. They used a ruby laser to pump the medium. Ruby laser, as you know, of course, used another pump laser, another flash laser to pump it. So the flash laser was the incoherent source, the ordinary conventional source, which pumped a ruby. Ruby gave a coherent beam of light, and then that coherent beam of light was used to pump another, which is the dye laser. So this coherent light of the ruby laser, once it pumps the dye laser, would be converted into another coherent source of light. But now this coherent source of light will be tunable. And near-infrared dye was used as the lasing medium. It is this provided output in the near-infrared region. So maybe we have to see what was the wavelength. So let us now concentrate on the energy level diagram to understand the operation of dye laser. What were the participating? But before that, let me mention here that a molecule can have two types of electronic states. One is a singlet state, the other is a triplet state. What are singlet state and what are triplet state? And by the way, this singlet state and triplet state play very contrasting roles in the operation of a dye laser. The triplet and singlet states are categorized depending on the orientation of the spins of the electrons that make up the system. When spins of all the electrons are paired, that means there is no net spin. The resulting quantum state is called a singlet state. And when the electrons have unpaired spins, that is characterized by a triplet state. So the two electrons are parallel spin, unpaired spin. It is a triplet state. The ground state, ground electronic state, is usually a singlet state. In the ground electronic state, spins of the electrons are always paired. Therefore, triplet state doesn't exist in the ground electronic state of the molecule. And the excited state involving an excited electron can be both singlet as well as triplet. So I end here today, and next class we'll begin from here. That is the energy level explanation of the working of a dye.